Hi there, I'm Dr. Nathaniel Davis. I'm a lecturer in physical chemistry at Victoria University of Wellington. I'm also an associate investigator at the MacDiarmid Insitute, and also coincidentally a member of both the New Zealand Institute of Physics and the New Zealand Institute of Chemistry. And in this brief presentation, I'm quickly going to talk to you about sort of the blurring of the lines between different research fields and how the physics of the future is going to occur on the edge of the field or between research fields. So cutting edge science occurs on the edge or between research fields is what we're going to be talking about. So firstly, a little bit about myself and how I've explored many fields of science. So education and the fields of science is quite fluid, and it's not as structured as you might sort of be led to believe during high school. So in high school, I was interested in biology and chemistry, so I started off doing biology. Then when I moved to university, I was doing molecular biology, genetics, and then sort of realized that I sort of enjoyed chemistry more, so moved into chemistry. And then my PhD was in physics, and now I teach chemical physics. So I teach sort of physical chemistry, and so there's all these connections between the different fields of astronomy and maths connect to physics, biochemistry is between biology and chemistry, and so on. There's really interesting research to be done in between these fields and combining them all. So what I work on is solar energy. I'm going to briefly talk to you about two aspects of how physics can improve solar energy. So if we wanted to improve solar energy, what could we do? We could either, one, make it more efficient, or two, make it cheaper. So just a brief bit of background to catch everybody up. So we know that the sun emits light, and these lights come in the form of photons. We have high energy photons, which is sort of your blue and your ultraviolet light, and we have low energy photons, which is sort of infrared and red. And so the difference in the energy is based on the frequency of the wavelength, and the visible spectrum goes from blue to red. That's sort of what a solar panel absorbs, and it's what we're interested in looking at. The only other bit we need to know is that orbitals can absorb photons. An electron can move from one state to another state with the addition of the energy of a photon, and when it emits that photon, it can luminesce or fluoresce that photon. So photons can use to move electrons up and down different levels of their orbitals. So how a solar panel works is you just have light coming in. Those photons promote an electron from the valence band into conduction band, and then what you do is you make sure it doesn't relax through your solar panel, but actually relaxes around and goes off and does some work, which is electricity. So that's all a solar panel is. Its light comes in, promotes an electron across this band gap, is equivalent to an orbital, and instead of relaxing down, it has to go and do a bit of electricity. But the problem here is that you might have noticed is the sun up here is putting out photons of lots of different energies, and our solar panel only has a single energy level. This is called the band gap of the solar panel. And so then there's three different cases. The first case here in the middle is the perfect case, where the energy of the photon equals the band gap of your solar panel. So that means all the energy of the photon gets turned into promoting this electron across the band, and you get your electricity out. The other two cases aren't so good. So if the photon doesn't have enough energy, there's not enough energy to promote this electron and nothing happens. And if the photon has too much energy, you still get this extra electron, but it means that any of this excess energy here and here gets wasted and just heats up your solar panel. So this is what they define as a Shockley-Queisser limit. But simply this means that there's a trade-off between making your solar panel small to absorb lots of photons and getting excess energy as heat, or making your solar panel have a high band gap, but then you don't absorb as many photons. And this leads to a trade-off of either being big or small, and you get to about a 32% limit. The easiest way to think about this and the way around it is imagine you have a forest. So you have a forest, and it's full of big trees, medium trees, and small trees. And I come along and ask you to cut down all the trees, and you cut them down. And then I say, I'm going to buy your trees off you, but I'm only going to give you $1 for anything above a meter. Money. And that's basically what solar panels have done. So instead of allowing us to wait for the trees to grow, and we could have got them all the right size, like foresters do, we have to harvest them at a certain stage. So the sun's putting out energy of all these different photons, all these different trees, and we can only get $1 or one electron out of the right energy. So it's a pretty simple idea to think about what you do next to improve the efficiency to sort of break this limit. Would be start cutting trees in half or gluing them together. So you could take your 2-meter tree, you could cut it in half to make two 1-meter trees, getting $2 or 2 electrons, and you could glue 2 trees together, 50 centimeters, to make a 1-meter tree to get $1. And that's what researchers have been doing. So what we're looking at doing now, and involves quite a bit of physics, is adding together two low energy photons to make one high energy photon. Allows us to get the right amount of energy, or getting these high energy photons and cutting them into two low energy photons, shown here. And if we do this, we get up to about sort of 45% limit if we start doing this. And so without going into too much of the physics, because it actually does get quite complicated, you can see that there's a variety of different ways of doing this. You can add photons together or cut them in half using different sort of principles here. But the easiest way to see this, we're adding photons together. So this light here is actually infrared. It's about 980 nanometers. So it's not shown on this visible chart down here. My phone thinks it's purple, but that's just because of the phone filters. And what happens is when we put our solution in together, right, we actually get orange light out here. So in this case, we're taking two photons at 980 and getting sort of light out at 600. So these are processes that work. You can add together and cut photons in half. The second thing we could do is the simplest cost reduction. And the simplest way to reduce costs is to use less of a material. And so this is where luminescent solar concentrators come out. So imagine a piece of plastic or glass, say a window, that has luminescent molecules in it. Remember from right at the start here, we know that photons can promote an electron to a higher energy state, and when it drops down, we can emit another photon. So these are simple systems that start glowing. As you can see, light can come out because the photons are going in and out. So we've got these molecules that absorb light and emit light, and because the light is emitted within the glass due to the refractive index change, it's actually trapped and focused to the edges. So now you have a window where all the light hits it, ends up on the edge. And what you do is you just wrap a solar panel around the edge like so. So now instead of needing a meter squared of solar panel, you only need a couple of centimeters squared of solar panel. So it's a lot cheaper. You then just take this, you put this in the frame of your window, and you can start coating all your skyscrapers with solar panels, because instead of needing to expensively coat the whole surface, you're just putting tiny little edges of solar panels. And so to do this, you need molecules that glow, because you want to make these pieces of glass or plastic where the light comes in and glows out the side. So these are just some of the ones I have here at home with me. But as you can see here, they're glowing around the edges. So what we do is you put the molecules in, you shine light on, and you see they glow out the edges. And so biology, this is where we sort of start blending the fields together. Nature's very good at making structures. It's had millions of years of evolution to design these complicated structures. And in this case, you have like an energy transfer process here that means that all the light in comes out at a single wavelength. So a very efficient energy process here. We try to do similar things by making these molecules glow. And it's a combination of everything. So we use biology to inspire us. We then use chemistry to design our molecules and our scaffolds, so we have to actually build the things, and then we use physics to study the energy interactions. So in this case, all the structures here is chemistry, all the little wavy arrows here are energy transfer processes, that's physics, and then we're using biology to inspire us. So it's bio-inspired, chemically synthesized physics is what's going to be used to sort of make solar panels cheaper. So hopefully that gave you a little insight into sort of the research I do, and also how that it doesn't really matter where you start out in science. You can always branch between them, and you can reskill, and you can use your previous experience to sort of add to the field you're in. It doesn't have to be as clear cut as biology, physics, and chemistry. So thank you very much for listening, and have a good day.